Right. So in the last class, we introduced this new problem of lossy compression. Recall that in lossy compression, our goal is to compress an IID source sequence xn. So far, we are assuming that this xn is drawn from a finite alphabet, script x. Right. So we observe this memoryless source xn, and the goal is to represent this using k bits such that we are able to reconstruct some xn hat which is kind of close to xn. Right. Unlike lossless compression where we wanted xn hat to be equal to xn either always or with high probability, in this case it's only enough for xn hat to be sufficiently close to xn. And how close xn hat is to xn is measured through this distortion function or the distortion measure. For example, this could be the absolute error measure or the squared error or the Hamming distortion. Right? So we have one of these distortions which is fixed beforehand. So for a given distortion measure, our goal is to design this lossy compression scheme which ensures that the length of the compressed sequence is as small as possible. At the same time, the distortion is at most some quantity capital D. All right. So the goal is to construct an encoder-decoder pair such that the expected average distortion is less than or equal to some quantity capital D. And for a fixed distortion level capital D, we want to make sure that the rate is as small as possible. And in particular, we want to know what is the smallest achievable rate for which we can make the distortion less than or equal to capital D. All right. So what we'll eventually show is that the optimal rate will be given by a mutual information. All right. So how do we show this? So first we want to analyze some particular coding scheme. One way is to look for the optimal coding scheme directly that minimizes the rate. But instead of doing that, we'll use the following approach where we'll see what will happen if we picked a completely random scheme. Right? Well, random in the sense the distribution is carefully chosen, so there's some structure to it. But otherwise, we are using a sort of the code book, for example, is going to be generated completely randomly. Okay, and for any fixed distribution, a coding scheme can be completely specified by two things. One, the code book, which is the set of all possible reconstruction sequences or code words. Right, so this is what I call the code book, which is a sequence of 2 to the nr, or it's a collection of 2 to the nr sequences, all coming from xn hat. So these are the possible outputs that the decoder can output. So we're using a rate R compression scheme, which means that the decoder can output 2 to the nr possible different sequences. Right? And all possible sequences that this can output is what we call the code book. So that's one part of the compression scheme. The other part of the compression scheme is how do you map each source sequence to a particular code word or a particular sequence in the code book. And that is described by the encoder. Right. So the encoder that we will choose is going to be this joint typicality encoder. So we define this jointly typical set. So for a given joint distribution between x and x hat, for a given p x hat, this is the set of all pairs of sequences for which the joint type, that is the joint type is basically the empirical frequencies of all possible pairs of symbols in these two sequences. So the joint type is close to the joint distribution between x and x hat. Right? That's how we define this jointly typical set. And the encoder does the following. If there is one sequence in the code book for which xn is jointly typical with that particular sequence, then it outputs that sequence. And in particular, it's going to choose the first sequence in the code book which is jointly typical with this particular source sequence. If there is no such sequence, then it just picks some random sequence. We don't care. All right? So we want to show that it is indeed possible to achieve the expected distortion to be less than or equal to d asymptotically. Now, this is not possible for all possible r, but then we'll try to determine for what all rates r we can actually achieve this distortion less than or equal to capital D using this class of compression schemes. All right? Any questions related to the design of the compression scheme? So remember, we're picking the code book completely randomly, independently of the source sequence. So you generate a random code book. This code book is known both to the encoder and the decoder. All right? And the decoder and the encoder basically uses this jointly typical set to encode. All right? So before we go ahead and analyze the actual distortion that you can achieve, let's look at this jointly typical set and analyze its properties. Now, a lot of the properties of this jointly typical set essentially come from the properties that we've already derived for typical sequences. Because the jointly typical set for a joint distribution inherits all the properties that the typical set has for a given distribution, because you can just combine pairs of symbols together to form one super symbol. Right? So let's note these things down. So basically what we have is this pair x comma x hat, right? And what I could essentially do is map this pair x comma x hat to some super symbol y. All right? It's nothing else. I just relabel this pair x comma x hat to one symbol y. Right? So Px x hat can essentially be identified with some PMF Py. So the typical set corresponding to Px x hat is just the typical set corresponding to y. Right? So there's nothing new going on except for a relabeling of the alphabet. That's it. So now, given what you already know about typical sequences, let's try to answer the following questions. So if xn hat is has IID components drawn according to pxx hat, then what is the probability that the pair xn hat does not belong to the typical set? So recall, for the typical set, we had proved the following property. Right, for that, the probability that xn drawn IID according to px does not lie in the typical set is less than or equal to 2 times the size of x times e to the minus n times p min epsilon square divided by 3. Right? So what can we say for the jointly typical set? Correct. So 2 times the cardinality of xn cross xn hat, which is just the product of the sizes of x and x hat, times e to the minus n times p min epsilon square divided by 3. Where p min is equal to min of x comma x hat. All right. So the second property, what is, so if you have a pair of sequences that lie in the jointly typical set, and you have any function g, then the average is going to be the epsilon close to the expected value of g. Any questions? So there's nothing new, particularly new going on here. This is just a corollary of what we have already seen for normal typical sets. Similarly, if you have a pair from the typical set, then the probability of occurrence of that particular pair what do you think this should be close to? Correct. So it should be roughly 2 to the minus n times the joint entropy of x and x hat. Similarly, what can you say about the size of the typical set? How large should this be? So it should be 2 times, roughly 2 times n time, 2 to the n times the joint entropy between x and x hat. And the last part, suppose I have xn yn or xn hat which have IID components but drawn according to some distribution qxx hat. Then what can we say about the probability that xn hat lies in the typical set but defined according to pxx hat? So it's going to be roughly 2 to the minus n times the KL divergence between P xx hat and qxx hat plus some function of epsilon which goes to 0 as epsilon goes to 0. should be a plus little of 1. We won't particularly worry about what this function is. It's going to be something that is linear in epsilon with the constants depending on pxx hat and qxx hat. But it's not important because this is some quantity that is going to be very, very small when epsilon is small. Any questions? Okay. So an important special case is when xn hat are independent of each other. So xn is drawn according to px, xn hat is drawn according to px hat, but xn and xn hat are independent of each other. So basically they are drawn from the product distribution px hat. Then what is the probability that xn hat belongs to the typical set for pxx hat? So basically it follows from the above, right? So it's the KL divergence between pxx hat and px hat, which is nothing but the mutual information between x and x hat. I'm sorry?
What is Px?
So pxx hat is some joint distribution. All right? Doesn't matter what that joint distribution is. We are defining this typical set according to that joint distribution. But now suppose that xn and xn hat are drawn independently of each other, with xn being drawn from the x marginal of pxx hat and xn hat is drawn IID according to the x hat marginal of pxx hat. Right? That's the scenario that we are looking at. Any other questions? Okay, so now we essentially have all of the tools to analyze the performance of our coding scheme. All right, so remember that I have a code book consisting of 2 to the nr code words. Where each xn hat has IID components drawn according to px hat. Okay, and I mean even before that we've chosen So we're given, remember that x hat is coming artificially, right? The source is described by px. So for fixed source distribution, and we've also fixed a d, and we choose a small epsilon greater than 0. All right, so d is given to us. That's part of the system design problem. Px is also given to us. That's also part of the design specification. And epsilon is something that we have chosen. That's very, very close to 0. And we're also choosing px hat given x such that the expectation d x hat, when x and x hat are drawn according to px hat, remember that this is px hat given x. So px is given to us. Px hat given x is something that we are choosing. All right, and we're choosing one such px hat given x such that this expected distortion is less than or equal to d divided by 1 plus epsilon. All right, if you want, let's just choose this to be equal to d divided by 1 plus epsilon. Question? One thing to note is that this is the expected distortion between a pair of random variables that are drawn according to this distribution. This has nothing to do with n or the actual construction of our coding scheme. All right, this is some number, this expectation, and you compute it just using this distribution and this distribution. All right. Any questions? Okay, so we have chosen this particular distribution, and based on the marginal of this joint distribution with respect to x hat, we get px hat, and the code book is drawn IID according to this particular px hat, and it's drawn independently of the source. Right, independently of everything else, you generate this particular code book, and this code book is given to the encoder as well as the decoder. All of this is part of the system design process. All right. Now, what does the encoder do? The encoder sees a random sequence xn. It checks if this random sequence xn is jointly typical with xn hat of 1. If it is, then it outputs 1. If it is not, it checks if xn is jointly typical with xn hat of 2. If yes, then you output 2. If not, you keep proceeding one after the other. In the end, if at the end it checks whether it is jointly typical with xn hat of 2 to the nr. If yes, then it outputs 2 to the nr. If no, then it anyway outputs xn hat of 2 to the nr. Because it's not jointly typical with anything, it just outputs this particular sequence, just gives up, and it outputs 2 to the nr. Okay, so that is how the encoder works. So now let's try to analyze what is the expected distortion that is achieved by this particular coding scheme. All right. Now, to analyze the distortion, we'll take two cases. Case 1 is when there is at least one code word in the code book which is jointly typical with xn. The second case is where there is no code word in the code book which is jointly typical with Xn. So let's write this as expected value is expectation. Just to simplify notation, so let me have an event E So this is sort of the error event. It's a bad event. The bad event is that there is no code word which is jointly typical with the source sequence. So what sources of randomness does this event depend on? Where is all of the randomness coming from? What about Xn? Yeah? Correct, but I mean, so more specifically, what is the distribution with respect to which we are calculating this particular probability? What are all the sources of randomness that determine whether this event has occurred or not? So what are the sources of randomness in the system? There are two sources of randomness. One, the source itself. The source is drawn IID according to Px. And the second is from the code book, because we're choosing the code book randomly. And the code book, remember, is chosen independently of the source, but each component of the code book each component of each code word of the code book is drawn according to Px hat, independently of Xn. Right? So if you look at this particular pair, what is the joint distribution of this particular pair? So this is the source sequence, and this is one particular code word sequence. They are independent of each other, right? Because the code book is generated independently of the source. So this has IID components drawn according to Px hat. Right? Because we've chosen the code words independently of the source. Any questions? So there is this Pxx hat. It is some distribution that we have artificially constructed. From this joint distribution Pxx hat, there is a corresponding Px which is given. There is also Px hat which is obtained by marginalizing out x from this distribution. All right. Using this Px hat, we generated the code book independently of the source. Okay. So this Pxx hat is something that is out there, but none of these random variables are drawn according to Pxx hat. Okay. The joint distribution Pxx hat is used to construct the typical set. It's used to define the typical set. But none of these random variables are drawn actually according to px x hat, because there's no dependence, right? Your code book has to be independent of the source. Okay? Question?
Code words in the code book
Yes.
are distributed according to px hat.
Correct.
And px hat is coming from marginalizing the joint distribution.
Correct.
The joint distribution is chosen based on px hat given x. Joint distribution is constructed from
The joint distribution is some distribution, right?
but it involves px,
Uh,
which is the source distribution.
Okay, so, but how are these sequences actually distributed? This pair.
Px into px.
So xn and xn hat of I.
They are the product of px and px.
Correct. Yes. Right. But the joint distribution of this is not pxx hat.
Yes.
It is px times px hat.
Yes.
That's all the point that I'm trying to make.
But it depends on source.
Which one?
The distribution of xn and xn of y. It has a term px.
Which has a term px?
The table.
Correct, exactly. So because this is distributed according to px. The only point I'm trying to make is that they are not correlated with each other. Right? Because the way we have chosen px hat given x, there is some correlation. But these random variables, so the point is that these random variables are not chosen according to px hat given x. They're chosen only according to px hat. Okay?
px hat given x should be 0.
Which?
Sorry, it should be just px hat.
Which one?
Px hat given x.
No, it is not. Right? So, okay, the thing is, maybe the confusion is coming because of sort of a reuse of notation. All right. So let's maybe do the following. All right. So I have a px hat given x. Let us use a different notation for the code words. All right. So let's define if it makes things simpler. So let us define the code book. Which consists of code words, let's say yn of 1, yn of 2, and so on. Yn of 2 to the nr. I'm just using different notation where each yj of I comes from this alphabet script x hat, from the reconstruction alphabet, and each component of y of I is chosen independently of everything else, independently of each other, and they're all drawn according to the distribution px hat. Okay? So it's drawn according to the marginal px hat. Okay. And the output, let's say, this is equal to yn of I if where I is the first such that xn yn of I belongs to the jointly typical set specified by pxx. If no such I exists, then you take I equal to 2 to the n. Any questions? So now what can you say about xn and yn of I for any particular I?
Somehow, we are looking there, I is the first.
Yes.
It is the index of the NR matrix, right?
It is an index of this particular code book, right? So this is the code book, right? You have yn of 1, yn of 2 up to yn of 2 to the nr. It is the first sequence in this code book such that xn yn of I belongs to this typical set. Okay. So remember that this typical set is a huge set which contains roughly 2 to the n times h of x hat many sequences. You check if xn comma yn of 1 belongs to this, is one of these sequences. If not, then you move to 2. If not, you move to 3, and so on and so forth. Okay. So now what can you say about the joint distribution between xn and yn of I for any I? So it's px times px hat, right? So basically xj and yj of I are drawn according to the distribution px hat. To be completely precise, this is equal to product I equal to 1 to n px of xi px hat of yi.
When we consider like all possible combination of x and y,
Correct.
so it would be less than the entire combination in the joint distribution.
I'm not sure what you mean by that.
So the joint distribution xy for x hat
Yes.
will have a larger number of points.
So the point is that this the actual correlation in that defines Pxx hat is kind of artificially constructed. Right?
So what I need to say is I can sample x and y, okay, x and y from px into px hat,
Correct.
and also joint distribution.
You're not allowed to do that, right? If these two were, if this pair was drawn according to Pxx hat, then it would mean that you're generating a code word depending on the realization of the source sequence.
Yeah.
But you're not allowed to do that, right? Because the decoder doesn't know the source sequence. The decoder has to be a priori given access to this entire code book. Right? This is generated beforehand, before you even see xn. So before everything else, before transmission starts, right? You generate this random code book and you share this with the encoder as well as the decoder. So think of it as, say, a transmitter and a receiver. These are separately spaced apart, right? The transmitter or the encoder has access to this entire code book. The decoder also has access to this entire code book, even before you see the first source sequence. And then maybe you have like multiple source sequences that you want to encode using this particular code book. Okay, so this code book has to be generated independently of the source sequence. Okay, because if you were to generate that depending on the realization of the source, then you are essentially cheating. Right? Because the code book cannot depend on the realization of the source. Right? It's not that you design a code book that works only for one specific source sequence. Right? It has to work in general for a random source sequence drawn according to Px. Right? Does that make sense? Any other questions? I mean, this idea of a random coding scheme takes a little bit of time to get used to, but once you stare at it for a little while, you'll get it. Right? So the important point here is that xn and yn of I are independent of each other, and they're drawn according to Px hat. Okay? So in particular, what is the probability that xn for any I, what is the probability that this pair belongs to the typical set defined by Pxx hat? We just saw this a few minutes ago. So it's roughly 2 to the minus n times the mutual information between x and x hat plus whatever, something very small. Question? Okay, great. So now I have this, I define this particular event E, which is an error event. Which is that none of these pairs are typical.
here what is yn? Previously
Same thing, same thing.
you have written xn right above. Xn hat.
I just relabeled the code words to call them yn just to avoid any other confusion. That's all.
Sir, in this we are when we are taking an event, and we
Huh.
have said that this event is independent of px and px hat.
The event is dependent on xn and xn hat.
They are both are independent.
Xn and xn hat are independent of each other. In this case, xn and yn are independent of each other.
Now we are taking the probability of this belonging to t and epsilon.
Correct. So when xn and yn are drawn independently of each other, xn drawn IID px, yn drawn IID px hat, what is the probability that this pair, which are drawn independently of each other, will lie in the set, or will not lie in the set Tn epsilon for all I. So basically all of the code words are not typical with, or not jointly typical with this random xn. Is this okay? So what will this probability be? One minus? So which term? 2 to the minus n. So it's basically 1 minus the probability. Let's maybe write this down. Probability that xn I'm sorry? Yeah, that's right. Yeah.
This one is not mine. This is your character. Is anyone found on the bench or something here?
All right. So, okay, let's continue. What is the probability equal to? This? Summation? Product, right? They're independent. All the yn of i's are all independent of each other. So it's basically the product I equal to 1 to 2 to the nr of this. Is this okay? So this is equal to 1 minus 2 to the negative n times the mutual information plus some vanishingly small quantity whole to the power 2 to the n.
When we
Yeah.
started this thing and get the event
Correct.
both are independent,
Yes.
we define code book. Our code book is given to us.
We define, so we're randomly choosing a code book. Okay.
So after that, like this event, then are we trying to? I'm not getting that. We are getting the probability of that.
So I randomly chose a code book. Okay. And then the source gave me a random sequence. Okay. I independently randomly generated a code book The source randomly generated a source sequence and gave it to me. And now I want to know that for my randomly generated codebook and that randomly generated source sequence, what is the probability that there is no sequence that I have generated which is jointly typical with that source sequence? Does that make sense? So there are two processes that are running over here. One is the process that generates the messages. The second, the process that generates the codebook. These are both operating independently of each other. All right. So with some probability, all things will be good. That is, for the code word, you will have for the message, you will have at least one code word which is jointly typical with it. So again, when I say jointly typical, you should think of the following scenario, that if they are jointly typical, then the distortion is going to be small. We'll see exactly why that is the case. If they are not jointly typical, then the distortion is going to be large. So the good event is that there is one jointly typical sequence. The bad event is that there is no jointly typical sequence. So in this scenario, what is the probability that I'll end up getting a small distortion? What is the probability that these two are going to be jointly typical with each other when they are generated independently of each other? Okay, that's the quantity that I'm trying to bound.
All of this is at the encoder.
Which one? All of this is at the encoder. So once you specify the codebook and the encoder, the decoder's work is fixed, right? Because the encoder just outputs a binary sequence which basically tells you the label of the code word. Right? The decoder has to just read off that label and output the code word from the code book. Right? Does that make sense? So the picture is the following. You have xn, which is fed to the encoder. So there is this code that is independently generated. So this is being generated independently, and this is being generated independently. All right. This quantity is shared with the encoder and the decoder. All right. And what the encoder does is it just checks xn with yn of 1, yn of 2, and so on. It sees, okay, is there something for which the distortion is small? Yes, yes, yes. If there is 1, then it just outputs that corresponding I. If no, then it just outputs 2 to the nr. And the decoder, it knows I, it knows this code book, and it just outputs yn of 1. That's all, nothing else. Okay. So, in a sense, this is what you would do in any such compression scheme, except that the only nuanced part here is that this code book is also being generated randomly. In general, this code book would be fixed, right? This is fixed beforehand. Right now, what I'm doing is I'm also randomly generating this particular code book. But it is assumed that this code book is generated much before this source is even seen. So it's independent of xn. Okay. Any questions? And the reason why I'm choosing this code book randomly instead of analyzing one specific code book is that I don't know how to analyze one specific code book. But then I can say something probabilistically if this code book is randomly generated. Our end goal is to show that there is at least one code book for which the distortion is small. And this particular approach will let us do that. All right? Any other questions? Is it clear? Question?
What is the side distortion?
If there is high distortion, then it is true to the NR, and that will happen with some non-zero probability. Right? And that's precisely what that's what we are trying to analyze. What is the probability that the distortion is going to be larger than d by 1 over 1 plus epsilon? Okay, and we'll look at exactly what happens to the distortion in both these two cases. All right. Okay, so this is going to be the probability that none of the code word sequences are jointly typical with the source sequence. I'll use the following bounds. So we have 1 minus x being less than or equal to e to the minus x. So this quantity is less than or equal to e to the power minus 2 to the minus n times the mutual information between x hat plus delta of epsilon plus little o of 1 times 2 to the n. Right? And this quantity goes to 0 super exponentially fast if r is greater than the mutual information between x and x hat plus this delta of epsilon. Alright. So if my rate is just above the mutual information, then the probability that there is no sequence which is kind of jointly typical with the source sequence is going to be really, really small. Remember, a D case has e to the power minus 2 to the power something. Alright. So it's not just exponentially fast, it is doubly exponentially fast. Okay, so let's use this to actually bound the distortion. Question, yeah. Okay. So the expected distortion is equal to the expected distortion when this error event occurs times the probability that the error event occurs plus the expected distortion when there is a jointly typical sequence in the code book times the probability that there is a jointly typical sequence in the code book. All right. So this is basically the bad event. And this is the good event. And let's see what is the value of this particular distortion when in both of these events, the good event and the bad event. We know that if the rate is above the mutual information, then this probability is very small, and therefore this probability is very large. So this is equal to expectation of d xn x hat n given the error event times something that's very small plus the expected distortion between xn and xn hat given the good event times 1 minus little of I. All right. So let's see what happens in the bad event. So in the bad event, we can't say anything about the distortion, right? It could be large because we don't know how the source or the code word sequences look like. So in this case, we'll use a very loose bound. So in this case, remember, we assume that for any x hat, the distortion between x and x hat is bounded from above by some value d max. So in this case, the largest value the distortion can take is just d max. It's n times d max divided by n, which is just d max. So this is max overall possible x and x hat of d and we are assuming that the important assumption here is that this quantity is finite. Some value could be something large, but it's still finite independent of n. So if you combine this with this particular part, then you see that the first term is vanishing in n. As long as the rate is greater than the mutual information between x and x hat plus this particular quantity. Now let's see what happens if there is at least one sequence in the code book which is jointly typical with xn. In this case, what can you say about 1 by n? This particular quantity. Remember that xn, I'm sorry, this should be j equal to 1 to n xj yj of I. where xn and yn of I belong to this jointly typical set. What can you say about this quantity? So a pair of yeah. No. So there is at least one I for which this happens, right? At least one code word for which in the code book, which is jointly typical with xn. So let's forget about distribution, everything else. You have a pair of sequences that lie in this typical set, and you're taking the empirical average of some function of this sequence. What should this be equal to? Or
Joint PMF of xj.
what do you mean joint PMF? This is 1 by n d of x j y j, right? So what did we see? Should be the expectation, right? If you go back to this property that we had over here, if you have a pair that lies in the jointly typical set, then for every function g, the empirical average of the function values is upper bounded by 1 plus epsilon times the expectation. And this expectation is taken with respect to the distribution pxx hat. So this is less than or equal to the expectation taken with respect to pxx hat comma x hat times 1 plus epsilon. Right? But how did we choose pxx hat? Such that this quantity is less than or equal to capital D divided by 1 plus epsilon. Right? So this is equal to capital D divided by 1 plus epsilon times 1 plus epsilon, which cancels, so this is equal to D. So if there is one code word, at least one code word with which is jointly typical with xn, then it means that you are going to achieve a distortion that is less than or equal to D. So these are that's why I call this the good event. If there was no such thing, then you will end up with a distortion that could be as large as D max. Right? And what we just showed was that the probability that the distortion is less than or equal to D is actually very small. I mean, so it's less than or equal to D is very large. The probability that you're in this bad event where the distortion could potentially be larger than capital D is actually very small. All right. So remember that this expectation was taken with respect to the joint distribution Pxn and Pc, where this Pc was the distribution with which you generated the code book. So it's going to be less than or equal to D plus something that is vanishing in it. Questions? So, I'm sorry? So there are two events, right? Remember that the expected distortion is equal to this quantity plus this quantity, right? So this is equal to d max times the probability of the bad event, or it's less than or equal to d max times the probability of the bad event plus d times the probability of the good event, right? And this follows from what we had over here, right? The probability of the bad event is anyway vanishing in N. So this is little of 1 plus the probability of the good event is something that tends to 1. So overall this is just d plus some quantity that vanishes as n tends to infinity. Any questions?
How is PC different from AX?
I mean, PC is basically, so C is a sequence of 2 to the nr code words, right? Each of which is generated according to Px hat. Any other questions? Okay, let's. We have about 5-10 minutes, so we'll have a short quiz.